Good morning. I wanted to introduce myself real quickly. I'm Jason Lin. I'm relatively new to the team. I'm the new Managing Director of Data Science and AI Initiatives in the CS Department. Thank you all for coming and welcome. Our first speaker, Emma Brunskill, is an Assistant Professor of Computer Science. She's a Rhodes Scholar, a Microsoft Faculty Fellow, NSF Career Awardee, and ONR Young Investigators Program recipient. Her work focuses on interactive machine learning and reinforcement learning, on algorithms for high-stakes domains like healthcare, education, and consumer interactions. Please welcome Emma.
Excellent, you just did the right thing. I'm delighted to be here today. I'm going to talk to you about some of our lab's works, which is thinking about reinforcement learning to improve people's lives. So actually, I'm curious, who here has heard of reinforcement learning? Because that answer is changing a lot. Yeah, so about a decade ago, almost nobody had heard of reinforcement learning, but that's changing. And I think part of the reason that's changing is for a couple big reasons that I'll mention. Reinforcement learning is the idea of agents that learn directly through experience, through trial and error. And the amazing successes we've seen over the last decade is, I think, probably one of the main reasons many of you are familiar with it, which is in successes like video games or in playing the game Go, where we now have sort of superhuman level performance. And so when I tell some of my colleagues, could we turn down the... Thank you. When I tell some of my outside colleagues that I work on reinforcement learning, they say, well, that's great, but I think that was done about 2 years ago. And why do they think that? Well, because when they hear about these amazing successes of, agents that can play video games or, beat the best human at what's considered an extremely hard board game, they think that maybe we're done. And I like this illustration from my colleagues at DeepMind about what is going on in the agent's brain when it thinks about how to play the board game Go. So when we think about AlphaGo and we think about these amazing successes, they have several different typical characteristics. In particular, these are very high quality simulators. So we know how to have an agent play a video game, and this can be done millions and millions of times without affecting anybody. And we can always try these things out, and there's only a few times where we really care about whether the system is working well. So we care about it when we're in that final match, in the game Go. We don't care about it during training. But if we think about sort of the use of reinforcement learning in healthcare or in education or in other domains where we might be able to impact people, then the situation is very different, because when we have algorithms that are learning from experience, if these systems are going to be used for students or for patients, then those decisions are affecting people. And so therefore that introduces a whole host of different technical challenges and opportunities. And so that's really the stuff that we work on in my lab, is I think about the full technical stack of questions that arise when we want to make reinforcement learning systems that can help people. And what I want to do today is just talk about two examples. We don't have a lot of time. So let me start with one, just a really quick overview background, and I won't do too much math in this thing, but I think it's useful just to frame sort of what do I mean by reinforcement learning at all. So we can think of these normally as a Markov decision process, where the idea is that you have some agent that's making decisions that are going to impact a person, and then we're getting some observations back. I'm often going to call that a state, though again, I'll try not to be too jargony, that gives us information. And then the key thing is our decision policy, which is a mapping from information about the world to what we should do next. So you could think of this as, given the patient's symptoms, do I prescribe them Tylenol or do I prescribe them Advil? And one of the key things that we assume is that we have some way to measure the effectiveness of these decisions, typically used as a reward signal, and that our general goal is to maximize our expected discounted sum of rewards. So in the case of a patient, this would be something like quality adjusted life years. So we can look at different measurements of how good are our decisions and then try to make decision policies that maximize those outcomes. One of the big challenges in reinforcement learning and in life is that we don't normally know the dynamics of these actions in advance. We don't have perfect models of the physiology of a person, and so we're going to be sort of using ideas from, say, physiology plus data to try to learn better models of how our decisions affect the state of the person. So when we think about reinforcement learning, this is sort of normally the standard setting we think about. We kind of have this box and we think about these decision processes, and this is what I teach in my reinforcement learning class. But of course, there's a number of really important things like, what is the action space? Am I only allowed to prescribe Advil or aspirin, or is there a larger set of interventions we could consider? And what is the state space? How do we describe the patient? And what are the features we're using to make those decisions? And these things historically haven't been considered quite as much. And one of my big interests is, what are these choices and how do they influence the type of performance that we could get in these cases? So let me tell you, I thought I was going to tell you briefly about two things. The first thing is risk-sensitive reinforcement learning. And I'm going to talk about this because normally when we care about these reinforcement learning systems, we care about performance on average. So if we were to run this system 1,000 times on average, how well would it do? But in many cases, we want to go beyond sort of averages. We want to think about the full distribution of outcomes that we might experience. This is important for two reasons. One is that for individual patients, they're only going to experience one outcome. I can't, try to prescribe people Advil and then rewind the clock and then try to prescribe them aspirin. So you can't, so any individual is only going to experience one linear life, so one trajectory or one return, and we might want to be able to make guarantees on the performance that any individual will experience. The other is that even if I'm an organization and I'm a hospital, I'm an insurance provider, and I am effectively averaging over many people, I may care about things like fairness or equity so that I can again assure that for any individual subset of groups that I can still make performance guarantees. So when we think about risk-sensitive reinforcement learning, people have thought about this problem in the past, but they've typically focused on a couple different sub-scenarios. So one is the idea that we're given some data and we want to plan kind of a safe decision policy. So this might be a decision policy that maximizes the worst case outcomes. So like in the worst case, this comes up a lot in finance, I still want to be able to retire when I'm 65. And I want to design a portfolio of stocks so that I'm sure that that will be possible. So not on average, but even in the worst case. A second thing that has come up a lot more recently is thinking about safe exploration. This is particularly important in robotics, and it has implications for healthcare as well, which is that while I'm trying to learn through experience, while I'm having systems that can interact in the world and gather data, I want to make sure that they don't make catastrophic mistakes. And in the context of robotics, this comes up because if you have a drone or you have a robot and you crash it, you can't do any more learning with that system. And so you need to do sort of more conservative exploration. The thing that I'm going to talk to you briefly about today is, well, what if we want to quickly learn a safe policy? So mistakes aren't catastrophic, but we'd like to sort of still find something that's going to work even in this sort of conservative case. So I think for things like thinking about like behavioral health nudges, this could be a good example because this is somewhere where if I make a recommendation such that it doesn't help people exercise more today, that's not catastrophic, but I would like to have something that for all individuals on average is helping them. So this is a problem that's been much less studied, and we started thinking about this with my grad students recently. And so I'm going to tell you briefly about a paper that will be coming out in a couple months. So again, what do I mean by sort of thinking about risk-sensitive reinforcement learning? This is where we're going to think about all the distribution of outcomes that could occur. So instead of just looking at the mean of this distribution, we're going to look at the full set of potential outcomes. So this again could be how much do people exercise or some other metric that we care about. Now, in particular, what am I going to care about inside of this distribution? I'm going to care about conditional value at risk. This is a particular measure of risk sensitivity. It's commonly used in finance. And what it looks like here is it says, what is sort of the average performance of a bottom tail distribution? So it's not quite looking at the worst case outcome that you could have, but it's let's look at the bottom 5% of things that could occur, and what's the average in that? So it's one way to sort of think about having a more risk sensitive policy. And so what we want to do is learn a policy that in that bottom sort of alpha percent, on average is as good as possible. So in order to do this, we draw inspiration, and I'm going to skip a little bit because we don't have a lot of time this morning, from when we're thinking about optimizing for average returns. So my lab has done a lot of work on this. There's been a lot of theoretical work on this as well as practical work of like, how do we have agents that with very little data learn a good policy? But those previous policies have been good on average. So what do we normally do in that case? We're optimistic. And I love this field because there's sort of results that being optimistic is provably optimal, which I remind my grad students of a lot. So the idea in this case is you think about optimistically, so this is in the average case, what is the best thing that could happen given the data you have so far, and then you make decisions according to that. The reason why optimism is powerful is that either you're right, in which case you'll be making good decisions, or you're wrong and you'll learn something, get new data, and then you won't be quite as optimistic in the future. So we can build from these ideas and think about this when we care about risk-sensitive behavior. So now the idea is that instead of being optimistic about the average, we're going to be optimistic about the conditional value at risk, and then we're going to act according to that. So you might say, how do we do that? The key idea is that if you have a limited amount of data, you can bound how far your estimate of the distribution is to the real distribution. So this is a cumulative distribution function, and you can see here that I have these sort of maroon bars on either side that say, I'm not quite sure what the CDF is, but it's somewhere within this range. And you can pick something that's optimistic with respect to your uncertainty. So in particular, we can think of sort of what is the original estimate of the function given the data you have, and then we can shift it down. I find shifting it down can sound a little bit misleading, so I think an easier way to think about it is the following. If you have an estimate of the distribution of returns, we're going to take that bottom percentage and we're going to pretend that's really good and shift it over. And when you do that, your new estimate of the worst case outcome is optimistic. Because you can see that that red bar there, the worst thing that could ever have happened, is now further up on the x-axis compared to where it was before. Essentially what's happening here is we're being optimistic to be conservative. We're being optimistic about the worst case outcome and using that to gather how we change how we gather data. So we can do a very similar procedure to before, and let me tell you a little bit about how this works. So I'll just specify that this can work in sort of high-dimensional continuous state spaces, so sort of approaches like deep reinforcement learning and distributional deep reinforcement learning can be combined with the ideas that we're doing here, and that's what we do experimentally. So one of the reasons why I picked this as a sort of an example of the work we're doing in my lab is that some of the simulation domains we look at are health-related. So in particular, we look at sort of a classic operations research one for machine repair, but we also look at structured treatment simulator for HIV, which looks at when you should turn on or off treatment, as well as a blood glucose simulator, where we're trying to keep people's blood glucose in a good range. So these are all simulators. The last one is one that's based on an FDA-approved simulator to replace early-stage animal trials. So it's a fairly good simulator. So what do we see in these cases? So in the case of HIV treatment, on the x-axis here is sort of how much data we have, and on the y-axis is how good is that conservative policy for doing sort of HIV treatment turning on and treatment off. And what you can see here is that our optimistic approach much more quickly learns a good risk-sensitive policy compared to prior approaches that are not strategic in how they try to gather data. Then if we look at sort of the blood glucose one, the blood glucose simulator is a nice one because it has a number of different patients in there. And so what we can do in this case is that we can, all of these algorithms have a small number of hyperparameters, just one. But in general, that's a challenge in reinforcement learning because we don't know for a new individual what those should be. So what we did in this case, again, on the x-axis here is the amount of data, y-axis is the performance of the policy, is we tried to tune these hyperparameters on one of the simulated patients, and then we fixed them for all the other patients we looked at. And so what you can see here is that regardless of the patient, we're always getting a significant lift in being more strategic in how we gather data for that individual. So if you think about this for sort of what we might do for a personalized medicine application, you can imagine that based on previous data, you would tune this hyperparameter, and this suggests that as the system was working with new individuals, in all cases our approach and being optimistic would much more quickly find a personalized policy for that individual. Now, so in all three cases, optimism was significantly beneficial. One question you might be wondering about, I mentioned this issue of safe exploration earlier, and that with the drone, we don't want to crash it. Well, we don't want to crash patients either. And so you might wonder about, well, as it's doing this sort of exploration, is that resulting in people having significantly bad side effects? And one of the nice things about having algorithms that are more data efficient is it means that you're going to have less bad side effects because it needs less data to learn. And so what we can see here is compared to sort of a less strategic and sort of efficient algorithm, eGreedy, we have many less cases where sort of our simulated patients experienced a significant medical condition. And we have other algorithms here where if one's really concerned about safety, you can actually directly bake that into the algorithm. Okay, so just to summarize here, I think that we can be optimistic to be conservative, and that doing so can allow us to need much less data in order to quickly figure out things like personalized policies for healthcare. I mentioned that I was going to talk about 2 examples. Another question that comes up is sort of what is the best we could hope for? So we were collaborating recently with a company that uses nudges to try to help people manage chronic health conditions. And one of the questions they asked me is they said, well, we have all these nudges, and you're going to help us do reinforcement learning to figure out what nudge to do at the right time, but we're not actually sure if these nudges are any good. So it might be that we spend 6 months and we do all this beautiful machine learning and optimization, and we figure out nothing is very good. And so this issue of thinking about, what is the action space? What is the space of interventions or nudges? And is that any good, even if you have the perfect decision policy, is a really interesting one. And so what we started thinking about in this case is if you're given sort of a set of features that say describe a patient and a set of interventions you're choosing from, what is the best possible performance of any decision policy? Given that that you're fixing the intervention set and you're fixing the way you're describing patients. And so if you have a way to parameterize that, in particular, we want to learn that quickly. And we were curious whether we could do that before we could even return that decision policy. So my colleague, Greg Valiant, calls it sort of sublinear regime. So we're trying to say, even before I could actually even tell you what that is, tell me if it's worth it to continue to gather data and to do any more optimization. And somewhat surprisingly, the answer is yes. So a colleague of mine has been thinking about this, and his recently graduate student, Wei Hao Kong, have been thinking about this for prediction problems. When can you need less data to figure out the predictive accuracy of a classifier than actually to return that? And we're showing we can do the same thing in the context of one-step decision making. That under some conditions, with less data than what you'd need to return any decision policy, we can tell you what the potential performance of any policy would be. So I think this is really exciting. Right now it's been sort of mostly in the theoretical side, but the algorithms we've done it on things like sort of a humor recommendation algorithm, and then also looking at predicting cancer dosing for another data set. But I think this idea of figuring out, when do we need to optimize and when do we need to change the interventions we're considering is a really important one. And if we can use machine learning so we can help sort of a human in the loop to decide when to make that call, that's really powerful. So just to summarize, my lab works on the sort of full technical stack of questions that come up when we think about applying reinforcement learning to situations with people. And if you'd like to discuss any of those with me, I'd be happy to. Thanks.
Thanks. So, I'm only vaguely aware of reinforcement learning, but from what I see, it's usually used in situations where you can get a really quick turnaround time and seeing if something worked or not. And with the patients, obviously you can wait quite a while. Do you sort of take that into account when you're doing your optimization?
Yeah, it's a great question. So we do take that into account. One thing we try to do often is to see if there's any sort of proxy rewards or other indications of success for our decision policies. But one of the big challenges in reinforcement learning, exactly as you mentioned, is this kind of delayed credit assignment. Like if you only can see outcomes in a year, if you have historical data in that case, that can be a really great place to start.